You should be aware of also with MATLAB. I'll show you. I go back to this 4x4 problem, and now pure A, not a sparse. Run it and crash it. So now I have this A matrix 16 by 16 with this structural form here. If A is now going to be big, you can't really print it out on the screen. So then it's a question, how does he actually look? Well, then you have a nice routine called SPY. SPY gives you a graphical visualization of your matrix. And you just put a dot if you have something different from zeros. So here clearly you see we have this nice 5-diagonal structure, as we should have. A little bit odds and ends, that's due to the boundary conditions then. Depending of course how you're numbering your unknowns. But at least easily you can see the system. And again, if I now create a sparse matrix out of A, so he is stored on this form, you can still use SPY. He still produces the same result. So as I said, commands involving matrices works with sparse matrices as well as ordinary matrices. SPY, that's a very good one. So I mean, if you now have something like a bigger problem here, where are we? What should we do? 40 by 40, and here I write now sparse directly and run it and crash it. So yes, you can print out your A matrix, but you really can't see it. Printing out the full matrix is going to take forever just to scroll on the screen, but SPY should now work very nicely indeed. So here of course you have to zoom in to see, do I have 5 bands here, or how many do I have? Yeah, I actually have 5 bands. 3 here, and then another band further out. So SPY, that's a very good one. Can recommend that one. Back to this problem. So I'm now solving this equation system. Double derivative equal to -1 for a solve problem. And now I use different methods to find an exact numerical solution. I use the MATLAB's built-in backslash. Coming back to that one later, because it's quite efficient actually. And I also have an analytical solution. Yeah, you've seen this one before, I think. So here I can find now the discretization error, actually, the difference between the exact numerical and the exact analytical. So I can actually have the error between those two, the discretization error. And I start solving the different, solving the system using different algorithms. So first one here, that's the steepest descent. So here you have the source code for steepest descent. It's really small. You have these 3 steps, and this is just for plotting, so don't worry about them. But I take the time here. That's a little unfair because I actually update the array here, which I haven't pre-allocated, so it's a little bit slow. But never mind that. Tick and tock. There's just a stopwatch in MATLAB. So here I have the pure conjugate gradient. Some more steps, but not much. then I wanted to use an omega, meaning SOR. So I have just made a lot of runs with different number of unknowns and finding good omegas by trial and fail. So here I just interpolate finding a decent omega for the SOR. So I have that one as well to compare with. Here I have then omega equals 1, meaning it will be Gauss-Seidel iteration. And down here, finally, I use the bi-conjugate stabilized routine as I found in MATLAB. So you have plenty of these inside MATLAB. Now here I'm going to use a preconditioner. And I use this ELU, incomplete lower 2 and upper 2, I call them here, from a routine that you have to prescribe some accuracy here, how to make a good A inverse to a certain degree of accuracy. But that means these matrices that I later is going to push into the conjugate gradient routine as preconditioners here, they will be quite big. They can be dangerously big. So that one we have to be careful with when we're using this this conjugate gradient version BSEG stuff. So let's try to run the code and see what happens. So it didn't take too long time. I have two figures. First, the residual versus the number of iterations. And here, the relative residual, this one is possibility then to get down to machine accuracy. Then you're solving the algebraic equation system until you can't get it any finer on your computer. 16 digits accurate solution. So you see the steepest descent is very bad, all the way up here. Even badder than Gauss-Seidel, which is very stupid indeed. SOR, well, decent behavior. The conjugate gradient, the pure conjugate gradient without any preconditioner, not so bad, but still 100 iterations was needed for this problem. Now, with a good preconditioner, you are here. I don't know how many this is, 5, 6 iterations. Then he has found the solution down to machine accuracy. So yes, these conjugate gradients can be very efficient indeed. Don't forget the waste you do by solving your algebraic equation system all the way down to machine accuracy. We have an adder already in our discrete equations, so if you look at a total adder, you see you could have stopped here after 50 iterations with the conjugate gradient. You didn't have to push him all the way down to machine accuracy, so he would be good enough already up here. The rest is waste of time. So we have the same image here. Here I couldn't print out the prehistoric, the history here from BSEG stuff, I only got the last one. So it's more than one iteration, it's 5 or 6 or something like that. Now, if we write whose, we have a lot of unknowns, and our coefficient matrix should be here somewhere. The A, 1600 by 1600, but it is a sparse one. Now look at L2 and U2. They are just as equal. These are the ones I now used as preconditioners. They are also sparse, but you see they are getting big. So if I want to investigate them a little bit more. Spy A. So this is the original coefficient matrix. Mostly zeros, sparse. So if I now write sparse, what was it called? L2. Whoops, I shouldn't write sparse, it was spy, sorry. Spy. Well, he looks quite small, quite narrow, but if you zoom in here, you'll see he has quite a lot of values. So definitely a lot of values different from 0. And now you can do some stupid choices here. If you demand higher accuracy for this lower upper incomplete matrices. So if we now write, say, 8. I'm not sure if he can handle it. Let's try it. Yeah, the B-Seggestab, well, still roughly the same amount of iterations. Maybe a little bit faster, I don't know, but the size now, well, no, actually it didn't change much. It was roughly the same, wasn't it? L2. Yeah, it didn't change much. A little bit. Now it's more full. And if you really want him accurately, then in the end this matrix is going to be completely full. And then you of course blow the memory again. Not from your coefficient matrix, but meaning you are trying to find the inverse of A. Okay, any questions so far? It's okay? Now back a little bit to this, what was it, up here? The backslash. The backslash, that is built in MATLAB, and they have built it very smart indeed. When you want to solve an equation system, AX equals B, of course you can write something like this. X equals inverse of A and then multiply with B. That should be a straightforward way. That's what we learned in math when you have it on the matrix system. You have to find the inverse of A and then multiply with B. Yes, you can do this. It takes some time, not too long, but he can handle it. So just now to show you, B equals inv of A. There actually he has solved the equation system. And now if you write spy to this B matrix, there you have it. So finding the inverse, that's a killer. So that is why MATLAB invented then the backslash. So A backslash B. He finds the solution much faster without blowing your memory. So that one is really efficient. And just to show you how efficient, I was actually quite amazed when I checked this one. I solved the same problem, exact same setup. And then I play around with different numbers of unknowns. So I end up with a 200 by 200 unknowns, the biggest problem. And then I just solve it. I have to set up the A matrix. and then just find this solution here. I just print out how long time does it take MATLAB just to solve this equation, nothing else. And then I store this time and plot it. So let's run that one and see what happens. So the small problems go pretty fast. 150 takes some time, 175. It's costing more and more. And then finally 200. So here now you have the what is it? The number of unknowns versus CPU time, as Tik and Tok reports it, and actually it's fairly close to a straight line. So that's a decent behavior, I would say. If we had continued with even bigger problems, then I think he would have started to slightly curve upwards. But I was impressed when I saw this the first time. So the backslash in MATLAB is extremely efficient. Very close to solving n equations with order n operations, linear behavior. And you can run this by, with some additional information, ask what actually he has done, and then he will return a lot of information. He has done a lot of checks, information about what he actually has done here to find the smart way to solve it. And if you look at the MATLAB documentation here, just have left the divide, you can actually read some of the theory behind this system. And trust me, well, it's not that much in this version, but they had a lot of information about it, at least in the previous version of MATLAB. There should be some references also somewhere. So he has done a lot, and the numerics behind it is sophisticated indeed. So trust me in saying this one is very, very efficient. The conjugate gradient routines, as long as you find the name of one, Biseggestab, you can go all the way down in help and find C also. Conjugate gradient squares. I don't remember all these names. So you have a lot of these routines and how they work and how you should use them. And here is quite possible to use them wrong, so that you will actually not find a solution. So absolutely worth a peek if you need an efficient solver in MATLAB. And here I think you have the source codes available. I mean, when you use a MATLAB routine, Biseggestab, let's see if that is the case. If you want to see how this one is programmed, it should then be possible to write something like this to find the source code. So a lot of these will be free. I'm not sure if the backslash is free. I haven't tested it. Well, we can check it. It's at least going to be a very big routine. Here, the Biseggestab, you can read everything how it's done. So quite advanced programming. MATLAB is actually getting fairly decent, I would say. Let's try edit ML divide, wasn't it? Yeah, he's here, but no code. So this is hard-coded, so you don't have the M files for it. So it's sort of an execute file in the background to speed it up. But at least you have some references for it here. Okay, anything else that you wanted to know about conjugate gradient methods? So that should then be the end of the fast solver in this course. I don't think I want to bug you with anything else. In practice for you guys, you don't worry about it if you're using a CFD package. It will be some of these routines in the background anyway. In OpenFOAM, for instance, you can choose whatever you want to use as solvers. I guess the same goes in these other codes. Fluent CFX, StarCCM. Choose your own solver. And there, maybe you are allowed to give him some of your own input, or if you don't think about it, you have no idea what he's asking about, you just use the default values. Normally that should work fairly well. But the idea here is to give you some insight into what these input parameters might be and what they might include. Like using a conjugate gradient with a very nice preconditioner. It will be efficient, but also you will blow the memory on the computer. Your choice. Okay, next topic in this course will then be finite volume, unstructured mesh systems. So I'll put out some old texts for you, a couple of chapters I stolen. The chapters actually are called Control Volume Finite Element Method. So don't worry about that, it's still finite volume. So the community is still fighting what's finite volume, what's finite element, and nobody can really tell the difference. It's a matter of opinion, so I call it finite volume. So it's a fairly simple interpolation within one single volume or one single element. So that should be the topic for next week. I'll put out some exam suggestion on the homepage and see if that can be swallowed by the rest of you. We had several possibilities, and I believe it would be interesting here to have it early. So I will at least suggest it, and then if none of you protests, I will send it into the exam office as a suggestion, and then we'll have to see what happens. So just pay attention to the homepage about the information for the exam date. Any questions? Then we stop early today.